Can you guys do differentiation really quickly? Sure. Can you do differentiation really quickly of the wrong thing? Yeah, absolutely. But here's what we've done so far. We've done things like this, fx and fy. What are those? That's the rate of change in the x direction and the rate of change in the y direction. Now that we're in 3 dimensions, though, how many other directions are there? Infinite number of other directions. So we've looked at going in the x direction, we've looked at going in the y direction, but how many other directions are there? There are many other directions. So what are we going to learn today? Anybody want to guess what we're going to learn how to do today? How to find d, like we're going to find some partial f in some arbitrary direction, in any direction. Hey, super cool. Are you excited? I'm excited. I'm super excited. So this is what we're going to look at right here. Okay, so there's, hey, that's a pretty cool sketch. Nice. You like that sketch? I like that one, right? So you see those 2 arrows? Those are the directions we've done derivatives in so far. There are lots of other derivatives that we could find. There are lots of other rates of change. In terms of practical application, if you're sitting on the side of a mountain or that's a temperature map, you might be interested in finding out things like what? If you were sitting on the side of a mountain or that was a temperature map, what might you be interested in finding in terms of direction? What's one thing you might be interested in finding? What's the biggest slope? Yeah, what's the steepest direction? Or what's the yeah, least steep. And it's interesting, we have to be careful now. Like steep could mean down or up, right? Yeah. Like steep could mean down or up. So steepness is like speed, it's the magnitude of velocity. In terms of a path, we might be specifically interested not just in the steepest, we might be, or the steepest in each direction, we might be interested in what? Like when you're walking on a path, what's the easiest type of path to walk on? Flat, right? So we might be interested in what direction do we go in to stay at the same altitude, right? But the point is, are those directions necessarily going to be in the x direction or the y direction? No, they could be in one of the other directions. Just a new thing that's going on in that difference quotient. What's changing? Which parameters are changing? What's changing in there? X and y. X and y are both changing. Before, what were we doing? We were fixing one and changing the other, and then switching it. In this case, what's changing? X and y are changing. There are a few things that are super important about this definition here. What do you think is, there's one word up there that's super, super important. Which word do you think is the most important? What was the thing you were continually just working to cancel? What did you want to get out of there? When you do the algebra on that, what do you want to get out of there? You want the h to get out of there. Why do you want the h to get out of there, Haruka? Why don't you want the h to be there? If you're trying to evaluate that factor, so we don't want h in the denominator. So it's all basically an algebraic quest to cancel h. And then once you cancel h, in the denominator at least, everything else should fall into place. So what does this algebra look like? Well, I could ask you this question right here. I could ask you, calculate the directional derivative of this. What shape is this, by the way? X squared plus y squared. What shape is that? That's a cone. Is it a cone or is it a bowl? What is it? Is it a bowl or is it a cone? What is it? Bowl or cone? Who thinks it's a bowl? Who thinks it's a cone? Okay. In the direction of the vector I plus j. So what was that word that I pointed out as being super important? Unit. So what's the first thing you're going to do if you're being asked for a directional derivative? Turn it into a unit vector. So what is I plus j? Well, I plus j, is that a unit vector? Yeah. Is it? What's the magnitude of it? Square root of 2. So how do you turn it into a unit vector without changing the direction? Divide it by its magnitude. So you divide it by its magnitude, and what do you end up with here? This is the direction you want to go in, and it is a what? Unit vector. And it is a unit vector. Okay, so check. We have our unit vector. So how will we apply this definition? Well, it's literally plug in time. It's literally plug in time. So what does it look like? Well, what point was it asking for? It was asking for the point 1, 0. So there's your 1, and there's your 1. And then you have the point 0, the y value is 0. So there's your 0, and there's your 0. You with me so far in terms of this algebra? So our derivative in the u direction is going to be f of this minus f of 1. So can we actually evaluate the function now? What is the function? It's x squared plus y squared. So what happens? You square, this is x right here, here's x. And what do? You square it, and then here's y, and you square it. And then what's f of 1, 0? 1.
So now it's just algebra. Hey, is that really nice that that cancels? Why is it really nice that that constant cancels? What was the whole goal? What was I asking Haruka about? If you can't get rid of those ones, you're not going to be able to cancel the h in the denominator. Once you get that, remember this? I'm sure you've done difference quotients like this, where if you go in reverse, if your goal is to cancel h, you want to get the constants out of the numerator. It always just kind of worked out, right? Exactly. In this case, does it work out? It does, because what does it cancel to? Oh, it cancels to this. And then as h goes to 0, what happens to this term right here? That goes to what? 0. And then what am I doing right here? Why did I multiply by that? What's that called? Yeah, I'm rationalizing. You know what? You guys don't have to do that. The only reason you're going to have to rationalize denominators is if, for some reason, the multiple choice gives you a rationalized denominator. They don't generally do that anymore in the AP exam. They don't generally rationalize denominators. So if you do, it kind of cancels. It's just square root of 2. It's kind of cool. So that's the limit definition. Do you remember doing stuff like this? Does this kind of ring a bell? You remember doing this, canceling h's? And it's really nice in that it gets you an answer, but can the algebra get really, really nasty? Like, for example, is this a relatively nice behaved surface? And yes, I'm using judgment words on math. Is that a nicely behaved surface? Generally speaking. Could I make that surface a lot worse? Like, what happens if I changed it to like x cubed, right? If I just changed, literally, if I just changed this to cube, does that change your algebra drastically? Yeah, like look down here. You'd have to start cubing stuff and then hope things cancel, and you really don't want to do that. So then let's go back to before AB calculus when you learn, after you learn limit definitions. After you practiced all your limit definitions, what was the next thing you were taught after you got limit definitions? What were you given next? Is the payoff right here. What does that say? What direction is u? The direction, what could it be? Any direction. So you have a function u. Right? So you're doing, if you have a direction u, and you're doing the derivative in that direction at the point what? AB. Effectively, what all that work above does is it takes the difference quotient, it generalizes it, it does all the algebra we just did, generalized, it crosses out the h's, and this is what you get to right here. When you do all the algebra generally, you get to this. And this is why it's so cool. What is this? The derivative in the x direction, u1, the derivative in the y direction, u2, but u1 and u2 have to be the direction you're going in, and it has to be a what vector? Unit vector. Has to be a unit vector. Why is this super helpful? Well, what does it allow us to do? It allows us to do the directional derivative without using the algebra, without using the difference quotient. So what did we do before? We did this question, right? And what was the direction? It was I plus j, right? So the direction, I won't say u, the direction was I plus j. So if we were to use this formula right here, so if I wanted fu, and now we get to say fu a lot, so haha, funny, 1, 0, what's that going to be? What's fx on that blue boxed formula, Andy? What's fx? What's the derivative in terms of x? 他教 any, 你不教 any, 他教. What is it? It's 2x. So what is? So it's going to be 2 times, what's the x value? 1, right? And then this was the direction, correct? Is that a unit vector? What's the magnitude of that one? Root 2, right? So what's the unit vector going to be? It's going to be 1 over root 2 I plus 1 over root 2 what? J. So this right here, what is u1? u1 is 1 over root 2. What is the u1 component of the direction you are going into? Nam, did that make sense, or was that a pleative? Oh my gosh. So we have 2 times 1 times what was it? 1 over root 2.
But it's not always the same.
No, it's not. It's not. You see, okay, that's a great question, Nam. I used an example where they ended up being the same. Do they have to be the same? No, it just happens that these are the same. So what is the next one? What's fy? 2y. And what's the y value on this point? What's the y? 0. So it's 2 times 0 times 1 over what? So what does this come out to be? 2 over root 2, which is? Hey, is that what we got before? Does that work match what we did before? Now remember, just because one specific example works doesn't mean that that's a proof for this. This work here is the proof for that statement. I want you to read it on your own to take a look at the notation. It's notation heavy. But the idea is this. If you take away one thing from the class today, you see that? That's what I want you to take away. I want you to take away that green box. But what's the key thing about the direction we're going in? Has to be a unit vector. It has to be a unit vector. It has to be a unit vector. Going in. Hey, what direction are we going in here? Hey, we're going in that direction. It says u equals, oh, whenever they use u, generally speaking, what do they have? What have they given you? Is that a unit vector? Is it a unit vector? Oh, come on, you can do it in here. Is it a unit vector? It's going to be 9 over 25 plus 16 over 25 is 25 over 25. So did they give you a unit vector? They sure did. So if you want to do 25 here, what is fx equal to on this one? Nam, what's fx? 25. What's fx? Just what? 2x, yeah. What's fy? Close. Negative 2y. So then what is fx at, what point are we dealing with here? 1, 2. What's fx at 1, 2? Careful. 2. And what's fy at 1, 2? Negative 4. Exactly. So what is the u vector? Well, the u vector is, what's a better way I should write it than how they've written it right here? How could I write it a little more clearly for our? Yeah, 3 over 5i, right? Minus 4 or 5j. So what is fu going to be in the at the point 1, 2? What's it going to be? All the numbers are there. What's it going to be? 2 times what? 3 over 5 plus what?
4. Negative.
It's fine. Negative 4 times what?
Negative.
How do you do? Is that okay? So what do we get there? 6 over what? 5 plus 16 over 5 is? How do we do? Did we do okay? Did we do okay? Okay, please do on your own 23, 24, and 26. Please do these on your own right now. I just want 3 answers.